Stoichiometry. What you'll see below is what I call the stoichiometry road map. What this means is it's a map, just like any other map that you would use, and you're going to need it to find the relationships between different units of things within a balanced chemical equation. You're eventually going to have to print this out, and I recommend you print it out in color. If you don't have access to a color printer, go ahead and print it out in black and white, and then color code it with either colored pencils or a highlighter or something so that you can clearly see the differences between the different ways to get from one thing to another. By the time that this lesson is over, you should be able to understand the three types of stoichiometric relationships, understand the mole, find and use mole-to-mole relationships to solve for unknowns within a balanced chemical equation, identify the types of stoichiometric problems, and understand that we're going to be converting within these stoichiometric problems with mass to mass, mass to volume, and volume to volume. I want you to recall from the last lesson about Avogadro's number. This is simply 6.02 times 10 to the 23 molecules, or it could be atoms, formula units, particles, photons, etc. And it's a way to directly relate that number to moles, to atomic mass units, and eventually to grams. When we talk about stoichiometry, we are talking about the term used to describe or relate different quantities of completely different units of products and reactants within a balanced chemical equation. We have mass to mass, volume to volume, and mass to volume problems. Within the mass to mass, you were given a mass of something, a product or a reactant, and we are asked to find the mass in grams of some other product or reactant within the same chemical equation. Volume to volume is when you're given a volume of a product or a reactant, and you're asked to find the volume of some other product or reactant within a balanced chemical equation. And then mass to volume, when you're given a mass in grams of some product or reactant and are looking to find the volume in liters of another product or reactant. We do this by way of molarity. So you'll notice that I have volume to volume problems starred. What you need to understand, and I want you to be very clear of, is that we are talking about standard temperature and pressure. STP is defined as 0 degrees Celsius and 1 atm. And when we have a reaction occurring at STP, we can use 22.4 liters equals 1 mole. I want you to be very clear that standard temperature and pressure is not the same temperature and pressure. Just because we have a reaction occurring under same temperature and pressures doesn't necessarily mean those temperature and pressures are 0 degrees Celsius and 1 atm. The mole, not the small burrowing mammal, it is a unit of measurement. It's just another way we have to relate two completely different things. We do this with money all the time. If I wanted to talk about a Japanese yen and its relationship to a US dollar, there's no direct correlation. But we do have ways to convert between them that allows us to relate them together. A mole, it's not a gram, it's not a liter, it's not an inch, it's not any of those common measurements you've heard of in your life before, but it is just another form of measurement. And it's a way that we can measure an amount of a chemical substance, maybe it's in grams, and then relate it to something else, say maybe a liter. It's the central unit of measurement for chemistry. So let's talk about the mole. We've already talked about Avogadro's number, 6.02 times 10 to the 23 atoms, or molecules, or particles, or formula units, etc. We can also say that this is equal to 1 mole. So if we know that 1 mole of carbon is equal to 6.02 times 10 to the 23 atoms of carbon, we also know 6.02 times 10 to the 23 atoms of carbon is equal to 12.01 grams of carbon. We get that number right from the periodic table. When we can say 1 mole of carbon is 12.01 grams of carbon, we call that the molar mass. the mass per mole of any element or compound. It's the relationship between the atoms and the grams of the element. So we can say the molar mass of carbon is 12.011 grams per mole, just like we can say that the molar mass of sodium, for example, is 22.989 grams per mole. Here's an example. How many molecules are in 0.250 moles of chlorine gas? Well, this is what we know. We know that we have 0.250 moles of chlorine gas. We know this because it's given right in the problem. We also know that there are 6.02 times 10 to the 23 molecules of chlorine gas. Why? Because that's our Avogadro's number for chlorine gas. You'll note when I said chlorine gas, you need to remember this format of the atom because it is a diatom. So if you always use this generic setup, you'll never get it wrong. You're going to have your given times any unit factors, sometimes there's one, sometimes there's many, will equal your unknown. So we can say 0.250 moles of chlorine gas times Avogadro's number over 1 mole, these cancel out, equals 1.51 molecules of chlorine gas. Now, I want you to be very careful. If you abbreviate too much and too quickly, you will find that this will sometimes look like this, even though molecules are completely different than moles. Be careful how you abbreviate. Just like money with quarters and dollars, we can convert back and forth between the relationships. We just did a given of moles and asked for molecules. Now we can take a given of molecules and ask for how many moles. So here, how many moles are in 3.28692 times 10 to the 23 molecules of oxygen gas? Well, I'm going to use the same process. I'm going to use Avogadro's number. Molecules cancel out. I'm left with moles. I end up with 0.546 moles of oxygen gas. We have a lot of stoichiometric relationships here now that we have a mole, now that we've introduced this. We can say Avogadro's number equals 1 mole. We can use molarity, which is concentration, as moles per liter. We can say 22.4 liters equals 1 mole, and this is only at standard temperature and pressure, STP. We can relate volume and moles using molarity, mole-to-mole relationships using a balanced chemical equation. One thing you should see here is that mole is the central. When you're thinking about stoichiometry, you should be thinking to yourself, how do I get to moles? So, how do we get to moles? What is the mole-to-mole relationship? We can start with a balanced chemical equation. And our coefficients from that balanced chemical equation directly tell us relationships between the reactants and products within a chemical reaction. So, if I have 2BF3, 3H2O, B2O3, and plus 6HF, what can we say about this? Well, we can say lots of things. We can say there's 2 moles of BF3, and if I use 2 moles of BF3, I will get 1 mole of B2O3. We can say if I need 1 mole of B2O3, I will also get as a product 6 moles of HF. They have a 1:6 relationship. I can say if I need 6 moles of hydrofluoric acid, I must use at least 3 moles of water. Their relationship is 6:3. Why does any of this matter? Now it's time to print out your stoichiometric roadmap. Well, back to our example. If you know you need, for example, 3.56 grams of hydrofluoric acid produced, how many grams of boron trifluoride would you need? There is no direct relationship between hydrofluoric acid and boron trifluoride except for their relationship within the balanced chemical equation, their mole to mole ratio. So this is what we know. We have 3.56 grams of hydrofluoric acid that we need to be produced. That's our given amount. We know that the relationship between hydrofluoric acid and boron trifluoride is a 6:2 ratio. 6 moles of hydrofluoric to 2 moles of boron trifluoride. This is going to be our first unit factor. We know the molar mass of 20.0063 grams per mole for hydrofluoric acid. And we know the molar mass of boron trifluoride is 67.82 grams per mole. Just a reminder, we get these numbers here and here by adding up the mass of each element within the compound. I need those molar masses so that I can get to moles. How do I get to moles? We get to moles with the molar mass. Then we relate the two different moles by way of the coefficients from the balanced chemical equation. Your strategy is given the grams of hydrofluoric acid, converting that to moles using molar mass of the hydrofluoric acid, then converting to moles of BF3 by use of the mole to mole relationship from the balanced chemical equation. Then we convert it back to grams of boron trifluoride using the molar mass. You'll see here, it's time for the math. There's my given, my molar mass of hydrofluoric acid. That lets me get to moles of hydrofluoric acid. Then I use my 2:6 ratio, my mole to mole ratio, to convert from moles of hydrofluoric acid to moles of boron trifluoride. And then I use the molar mass of boron trifluoride to get to grams needed of 4.0227 grams to use to get the desired product. You'll note as you look at the picture of my calculator there, I have taken the whole top row, multiplied it together, got an answer, and then I divided that answer by the whole bottom row, multiplied together. It's really important that you use parentheses when you're using your calculator because they 100% use order of operation only. So not having those parentheses present can sometimes be problematic. You might have everything set up perfectly correctly, but get a wild answer because you didn't use your parentheses. Parentheses are your friend. Now you try. Mimi is trying to figure out how many grams of oxygen gas she will need to synthesize 4.0 liters of nitrogen monoxide gas at standard temperature and pressure. Can you help? What do we know? We know that N2 plus O2 yields 2NO. Remember, it's oxygen gas and nitrogen gas, so it's in this diatomic form. Don't forget that. We know this is a volume to mass problem because we were given a volume, and it's asking how many grams Mimi will need. Our strategy is going to be liters of nitrogen monoxide, which is given, that's what we're trying to produce, to moles of nitrogen monoxide. We know it's at standard temperature and pressure, so we're going to use that 22.4 liters equals 1 mole conversion to get us to moles. And then we're going to convert to moles of oxygen gas, and then to grams of oxygen gas using molar mass. Here's the setup. 4.0 liters times our relationship, our first unit factor, which will get us to moles. Remember, how do we get to moles? Then we use the mole to mole relationship from the balanced chemical equation right here. You'll see there's an understood 1, and we know there's a 2. That is the mole to mole relationship within the balanced chemical reaction. And then we're going to go ahead and use the molar mass of oxygen gas to get us back to grams. And when we solve, we get 2.9 grams of oxygen gas that is needed in order to synthesize 4 liters of nitrogen monoxide gas at those standard temperature pressure conditions. That's it for stoichiometry. Next time, we will work on molarity.